All right, so your queue is a linked list. So there's a sentinel node, and it points to the head of your queue, which points to another node, and so on, until you get to the end of your list, which is where the tail of the queue is. So here's your queue. And your tree root is, you know, the usual stuff. So let's look at your linked list. So I'm going to have a struct, and I'm going to call these things queue nodes. So struct queue node. And what we're storing in the data piece of this queue is not a number, it's not an integer. Because if we store an integer and we remove that integer from the queue, we can't say, look at the left and right subchild of that integer. Integers don't have children. What we have to store in the queue is actually a tree node. So this queue node is going to have a struct tnode pointer, which I can call data, and then a struct queue node pointer, which we can call next. And our tree is comprised of struct tnodes, which is an integer piece of data, and then a struct tnode pointer, which we call left and right. So our sentinel points to the first node of our list, which is considered the head of the queue. The data piece of that is actually a pointer to a node in your tree. So when I say t equals remove, right, I want t to be a struct tnode pointer, and I'm removing the address of a node, and now if I say t arrow data, it's saying take the thing at that address, which is a node, and give me the data piece, or give me the left piece or the right piece. So you need to change your queue code from PA3 just a little bit. You need to change it so that instead of storing integers, it stores pointers to your tree nodes. And really the only change is in the declaration of the type of variables that you're using. When you prototype the function, when you declare the function, if you use temporary variables, right, they need to be pointers to tree nodes instead of integers. The code itself doesn't change though. But in practice, if you were to think about this, let's say your root of your tree looks like this. Okay, so step one, we insert the root of the node into our queue. So our queue kind of looks like this. Here's a sentinel. It's got something in the data, we don't care what, and it points to a node. And this node, it's the only thing in the queue, so the pointer is null. But the data that's stored in there is actually like this little tree. Now it's not actually a tree, it's a pointer to the root of a tree. But conceptually we might think of this as actually having this little tree inside here. And so now when we say step one, remove the head of the queue and set t equal to that, we change the sentinel to point to null, so we know our list is empty, and t is this little tree that we removed. So when we print t arrow data, that prints out a 10. And then when we say insert t arrow left, we're actually creating a new node with a little tiny tree containing a single node, which is 5. And we change the sentinel to point to that. So that's inserting t arrow left. And then when we insert T arrow right, we create a new node. The data is a tree consisting of just that 20. And we change the previous tail to point to that. So there's our little tree containing a 20, and now that's what our queue looks like. So you can come to this version of the world and kind of get a mental picture of what the whole thing conceptually looks like, but this is kind of a confusing level to work at. It's probably less confusing to think about your queue abstractly. It's a structure that I can throw things into and I can pull things out of, and I pull them out in the same order that I put them in. And the things that I'm putting in and taking out happen to be nodes of my tree. And try not to get bogged down on, is it a number, is it a pointer to a number, is it an actual node, is it the address of a node, right? Just think of it abstractly as it's a node of my tree, right? Which means it has a data value, it has a left and a right child. And so you can pull those out and you can put the children into the queue and so on. And this is a dance that you'll do again and again, especially in 223. We're going to be making more complex structures that are comprised of other structures, and we can always go down to the individual description of each structure and understand this is a pointer to a node which contains a pointer to a this or a that and so on. But if we can think about these things, these data structures, more abstractly, if we know what a stack does, we don't have to worry about the nodes that make up the linked list and the push and the pop operation. We can just think of a stack, or we can think of a tree, or we can think of a hash, right? So we'll get more practice with that as we go. The other comment I just want to make is that queue of integers, queue of struct T node pointers, almost exactly the same. None of your code is probably going to change for your queue manipulations, other than where you declare something to say integer data, it's going to say struct T node star data, right? It's really just the type of data. And if you wanted to make a queue of characters, all you'd have to do is change all your integers to char. And if you wanted a queue of strings, you change all of your chars to char star. And this is a really common theme in a lot of what we do in data structures. And it's common enough that a lot of languages such as Java have a concept called a generic. And in Java, what we can do is we can write code for implementing a queue, but we can make it totally generic, independent of the type of data that we're putting into our queue. And we can use a placeholder, and then when you want to use a queue, one time you basically say, okay, I want this to be a queue of integers. And internally, it basically replaces that placeholder with the keyword int. And now all your code works, assuming that your data is an integer. And now if you want a queue of pointers to heaps, you say, give me a queue where my data is a pointer to a heap, and it adjusts the code accordingly. And so this gets us into code reuse. So you're doing this manually here, but it's a general concept. All right, does that help with breadth first traversal? All right, other questions on this? All right, let me go through delete again in a different way. I can't tell you how disturbed I am that this is black and white. It's like eating about 40% of my brain.
Seriously, that's what bothers you?
Right now, yeah. There's about 5% of me that's hungry, 40% that doesn't want this to be black and white, and the rest is 222. So let's talk about deletes. So there's a few things to keep track of. So let's make a tree. or whatever. All right, so there's an essentially random tree. So the first thing is, suppose we want to delete, I'm going to throw one more node in here. I'm going to throw a few more nodes in here. All right. Suppose we want to delete the 20. This is a great tree now. Want to delete the 20 from the tree. Okay, the actual code you're going to write that finds the largest thing in the left subtree and replaces and all this other stuff, that only applies if we're deleting the root of a tree. Okay, we're not deleting the root of this tree, we're deleting a 20, which is down here. So all that code that we've been talking about doesn't apply yet. Okay, what your code is going to do is basically say 20 is smaller than 40, let's delete 20 from this left subtree. Okay, now when I get into delete and I pass it this tree and I say delete 20, it's going to say, 20 is the root. Okay, now I can actually do something. So let's just talk about how we delete 20 from this tree. So we're one level down in our recursion. When we're done, we'll come back to this and we'll finish up deleting 20 from this original tree. So let's just delete 20 from this tree. All right, so we'll come back to that. All right, so how do we delete a root? Our general prescription is go into the left subtree, that's this, find the largest number in there, that's an 18, and replace the root that we're deleting with the 18. So we're going to put 18 up here at the root. All this other stuff on the right is going to stay the same. And all this other stuff on the left is going to stay the same. Except the 18 has been deleted. Okay, there's one other thing we have to do, which was 18 had some stuff on its left. And since 18 is gone and it's already adopted 10 on its left, we've got these extra nodes that don't go anywhere. So the node right before 18, which is 15, is going to adopt these nodes. So this is going to pick up the 16 and the 17. So replace root with largest node on the left, which we're going to call L for large, and then L's parent on the right should be equal to L's children on the left. So 18 is the largest node, that's L. Put that up at the root, and then have its parent's right child become, instead of L, become whatever L had on the left. So L's parent arrow right becomes L's arrow left. And obviously do that before you move L up to the root, because once you move L to the root, its left child is, that 10. So order is really important in all of this. Okay, let's pop back up one level. We deleted 20 from this tree, and this is what we got. Here was our original tree that we were trying to delete 20 from. We deleted 20 from this purple circle, and we got this tree down here. Put that tree in place of this purple circle. Right? In other words, 40's left child was the tree that we were deleting from, so replace 40's left child with what we got as a return from delete. So that gives us our recursive code, which is the following. So delete returns a pointer to the root of the tree. So delete num from our tree. If num is less than tree data, then let's delete that number from the left subtree. Right, so our number was smaller than the root of the tree, so let's delete it from the left subtree. And then let's replace the original node's left subtree with that modified tree. So set tree left equal to what we got back from delete. Else if our number is greater than, then delete from the right subtree and set tree arrow right equal to what you get back from delete. Else, delete the root. And then when you're done, return the possibly new root of the tree. So the only real work you do is when you're deleting the root of the tree. If you're not trying to delete the root, either call delete on the left subtree or the right subtree. Set the left or right subtree equal to what you get back from delete. And then all your code goes in this else case where you're actually deleting the root. I strongly recommend that your delete function assume that the number actually exists in the tree. And so don't call your delete function until you've called search to make sure the number actually exists. So in your main program, if they say delete n, call search on n first. If n's not in the tree, you can say, hey fool, can't delete that, it's not in the tree. Okay, so now if you call delete on n, you're guaranteed n's in the tree, and it makes your code just a little simpler. And you can put that in the assumptions at the top of your comments for the delete function, warning, this function should only be called if the number is actually in the tree. And then the user has been warned. Good so far? Let's look at special cases, because there's multiple special cases. Alright, so I'll use some ABC for like bigger trees. So we've got, and we're only talking about deleting the root, okay? Delete the root. So suppose your tree looks like this. It's got a root, it's got some stuff on the left, and there's a number on the right, and those may have subtrees, and 20's got a potential subtree on the right. Okay, what's the largest thing in the left subtree?
15.
Guaranteed to be 15. Because there's nothing on the right and everything to the left is going to be smaller. So 15 is the largest thing, so we want to make that the root of the tree. So 15 will go up to the root. C will still be on the right. 10 will be over there. A will be over there. But in this case, 15 had a child on the left, so its parent 10 is going to adopt that on the right. So your tree should look like this. Okay, this is actually the same, probably the same case. We'll call this S for stuff, and then we'll call it P for previous, and then we'll put our 15 in here, and there's a B over there. So again, 15 is the largest thing on this left subtree. So that's going to become the root. It's going to have C on the right. This is going to have 10 and A. and it's going to have stuff, and it's going to have a previous node. And again, that previous node is going to adopt B on its right. So that's exactly the same as what we did here.
P is previous.
In this case, P was previous. In this case, 10 was what we're calling previous. So as you're moving down to find the largest tree node in the left, you've got to remember the node that came right before it, its parent or its previous node, so that that can adopt what your largest node has on the left. Okay, so here's an edgy case. If your tree looks like this, so there's a root, we're deleting, there's a node on the left, but that node has nothing on the right. So 15 is still the largest node in the left subtree, and it's got some stuff on the left, but there's no parent on the left to adopt that A stuff. So this is a special case, but it's a pretty easy case. 15 becomes the root, C is on the right, just hang A off the left, let it stay exactly where it is. The reason we have to deal with the previous is because if we move 15 to the root in this case, right, it's got something else on its left, and so its old left child is potentially orphaned. But if 15 is just the immediate left child, and it's the largest thing in the left subtree, you can just move it up to the root, put C on the right child. Okay, here's the serious edge case, where you don't have anything on the left. So you can't find the largest value in the left. So in this case, we just return this tree. In other words, we just change the root to be whatever the right child is of the root. That's the easiest deletion. But you only get to do it in this case where there's nothing on the left. I think those are all your cases, and like I say, these two are really the same. So I think it's really just the general case, the case where the largest value on the left is the immediate left child of the root, and the case where there's nothing on the left. So it's usually coded as 3 cases. Yeah.
Another case I could think of is that when the tree only has its root node, no left or right sometimes.
Ah, okay.
In which case it's turned to null.
Right. Which actually will work with this 4th case, because in this case C is null, so if I just replace the root with C, I'll be replacing the root with null. But you may have to code it a little differently as a special case, because it depends how you treat those nulls. You should never be trying to delete the root of a null tree, because remember, you're going to search first to make sure your node's actually in the tree. If you don't do that, you could say if the root's null, halt and catch fire or something. If it points to 2 things, like here, because we're deleting the 20 in each of these. So again, you find the largest thing in the left, replace the root with that. Probably the trickiest part of this is figuring out the largest node and remembering what the previous node is. So do a current previous kind of walking in step or something to let you know who the parent is of the largest node, and make sure you identify, if it's one of these oddball cases. And that's the algorithm you're required to implement. Okay, there are other ways you can delete, so don't do this. Right, did we delete the 20 successfully? Absolutely. Will you get points for that? No. Okay, you got to stick to this algorithm, because I want to know if you can code this algorithm. You could replace with the smallest element from the right subtree. That's a perfectly fine deletion algorithm. Don't do that. Okay? So, largest element on the left, unless there's nothing on the left, and then just move the root. And again, use lots of variables. Unless you really like the mental challenge, don't try to get too fancy with node arrow next arrow next arrow right. Right? If I call this node P and I call this node L for largest, the code writes itself, right? P arrow right equals L arrow left. L arrow left equals root arrow left. L arrow right equals root arrow right. Free root return L. Right? Just write the code to do each of these moves that you want. So it helps to have lots of variables. All right, other questions on deletes or PA4? All right, let's go back to heaps. So we did heaps. You inserted into heaps, you removed from heaps. And when you did this on the board, you put a bunch of numbers into a heap and then you removed them and you pulled your numbers out basically in order. It was decreasing order because it was a max heap. But this is something we can do with heaps. We can sort a set of data. So we can take our data, we can build a heap, we can pull the root out n times, and we've got our data in sorted order. And that works, but it's not as good as it could be. So when we insert something into a heap, it's basically order log n, because we put it at the bottom and then we have to upheap and get it into the right spot. And if we're building a heap of n numbers, we're doing n inserts, and that will turn out to be basically order n log n. And then we can remove, and to remove each number takes a single operation. We just read what's at the root, and then we go ahead and we move the last element up and we down heap. So that will be log n for each removal, but we may remove the root and start doing something with it in the background. Maybe we can adjust the heap. And so it may be very efficient to pull these things out and process them. For example, if this is a job queue, we can be reheapifying while we're processing the job. So I'm more interested in this business of doing these n inserts. And n log n is not awful, but we can do better. So if we want to build a heap out of a set of data, instead of adding the data one number at a time and adjusting the heap at each point, we can do something called heapification, which may not be a real word, but heapify is. So here's the idea of heapification. We take our numbers and we just throw it into something that's shaped like a heap without worrying about the heap property. And we throw all our numbers into this heap-shaped thing, and then we go through this process called Heapify, which turns this non-heap collection into a heap. And if we do this correctly, we can do better than n log n to heapify the entire chunk of data. So let's just make a heap of random numbers, a heap-shaped thing of random numbers. So I'll do 10, 20, 15, 5, 50, 2, and 12. So you just take your data that's unsorted and you just throw it into this shape. And it's certainly not a heap unless your numbers happen to be in decreasing order to begin with. So we're still doing max heaps here today. All right, here's how we heapify. We're going to start on the bottom row and we're going to move right to left. And then we're going to come up and go through the next row right to left. And then we're going to come up and go through the next row right to left. And we're going to keep moving our way from bottom to top, each row going from right to left. And at each point, we're going to look at the number and say, does this satisfy the heap property? Meaning, is it bigger than both its children? If it is, we don't have to do anything. If it violates the heap property, we're going to down heap. We're going to swap with the largest child, move down, see if that violates the heap property, and keep going. Okay, so how does this work? Does 12 satisfy the heap property?
Yes.
Yes, because it doesn't have a child bigger than itself, because it has no children. So 12 is fine. How about 2? Right, 55, those are all fine because they have no children. Okay, how about 15? Is that bigger than both children?
Yep.
Okay, how about 20? No. Okay, so swap with the largest child. Put a 50 here, put a 20 here. Does 20 satisfy the heap property?
Yep.
Okay, let's keep going. There's a 10. Satisfy or violate? Violate. Swap with the largest child, which is 50. Put a 10 down here. Does that satisfy the heap property? Nope. Swap with the largest child. Put the 20 there. Put the 10 down here. And we're done. We got a heap. So our new heap is 50, 20, 15, 2, 12, 5, 10. All right, let's do a really pathological example. And we want a max heap. Okay, is 90 okay? Right, doesn't have a child bigger, so that's fine. How about 80, 70, 60, 50? Those are all fine, right, because they have no children. How about 40? Nope, so swap with the largest. So this becomes a 90 and a 40. And 40 has no children, so we're fine. All right, come back here. There's a 30. Swap it with the largest child, so 70, 30, and 30 is fine. There's a 20, swap it with the largest child, which is 90. So 90 goes there, 20 goes here. Does 20 satisfy? Nope, so swap with the largest child, which is 80. There's our 20, and we're done. One more node, that's the 10. 10 is not bigger than its children, so swap with the largest. So there's 90 and 10. 10 is not bigger than the children, so swap with the largest, which I believe was 80. And the 10 goes down here, and 10 is not bigger than its children, so swap with the largest, which is 40, and 10. And now our heap looks like this, and it should be a genuine heap. So there's 80, 50, 40, 20, 10. And that's a heap. So that's what heapifying is. So you start off with a heap-shaped collection of data. Start on the bottom row, rightmost position, move to your left, and see if each node satisfies the heap property. If it does, don't have to do anything. If not, down heap, swap with the largest child, and keep moving until it satisfies the heap property. And then go on to the next number. At the end of a row, move up to the next row, start at the right, move over to the left. Okay, why is this better than just inserting your n pieces of data one at a time? I've got 9 things in this heap. The first 5 elements I didn't have to do any work on because they didn't even have any children. So 50% of your data doesn't need any adjustment. Now, this down heap process is arguably a log n process. And if you had to do this on n pieces of data, that's n log n. But half your data, you don't have to do log n things, you have to do 0 things. And if you move up one level, that's another quarter of your data. And at most, your down heap involves 1 swap. because after one swap, now you're at a leaf node. So 50% of your data, you do 0 things. Another 25% of your data, you do 1 thing. Another 12.5% of your data, you do 2 things. Only 1/8 of your data is going to involve more than 2 steps. The only time you're actually going to do log n steps is on one node, and that's the root. So even though on a back of the envelope calculation this looks like n log n, if you actually do the series, it turns out to be half your stuff does 0 steps, quarter of your stuff does 1 step, 1/8 of your stuff does 2 steps, and if you add it up, you end up with a total of n operations. So heapifying is actually order n, which is nicer than n log n. All right, so we got 7 minutes, so grab a spot on a board and let's build some heaps. And I will give you some data to put into your heap. So let's build a heap with those 7 numbers and then heapify it. Yeah, heapifying is throwing this into a heap-shaped tree, and then start from the bottom row, rightmost side, move across, and check the heap property at each point. If it's violated, down heap, and then keep going until you check the root, and then when you're done, you should have a heap. Down heap means swap with the largest child.
You go from right to left, and then you start checking. So these first ones don't have children. So they don't have children, so you go, these ones are fine. You go up, you start from the right side. So that one does have a child. Is that bigger than the other one?
No. So we're doing this one. And this one goes up to here. And we do compare this to again.
It's the way that you just put everything in. You just want to put it in. And then you sort it out. We were going through like every single time.
Yeah. Now she's saying go stop the line.
Sometimes it'll be even more.
So you're saying switch these two instead?
So 52, 5, 10, 1, 107. Yep, that's your starting point.
Start with this one.
And then start with the 70. And it has no children, so it satisfies the heap property already. So nothing to do for the 70. And then same for the 100.
So average stats for 32. Yeah.
And same for the 1 and the 10. All right, so now you go on to the 5. So, well, you check both children, see if it's bigger than both. If it is, you're fine. But it's not. So you want to swap it with the largest child. Okay.
Do we always insert the small stuff on the left side?
Nope.
No, okay, I see.
Yeah, nothing to do with left, right in this case. So, yeah, those are good.
Yeah.
Make sense?
I see it well.
All right, well, you got a few minutes, so turn it into a min heap. So So min heap is exactly the same thing. Start here, move over, go up, but at each point, you want each node to be smaller than its children. And if it's not, swap the smallest children and down. So if you start with that, you should be able to turn it into a min heap. Alright, makes sense? Alright, so now min heapify that.
This one, this side, or this side?
Exactly the same, but you're checking to see if the node is
From the
smaller
right,
than both
from the right to the
children.
left.
We start from right, but these are
Small,
children,
small.
so we can't compare these ones and do it. So we have to start off from this level. So 70, that's bigger. So we want. Yeah.
This hurts. This hurts.
So you're gonna heap it? Yeah, cool. Alright, all done. And you're heaping good. Alright, so that looks good. Go ahead and turn it into a min heap now. So min heap is exactly the same process, except each node should be smaller than its children. And if it's not, swap with the smallest child. So let's see, so you swap the 5 with the...
Because we want this.
Good.
Smallest,
Swap the
yeah,
two.
largest and
And good. Okay, so now you're looking at 50. Okay, so you're gonna swap it with 100. No, so you're going to swap this, and then you're going to see if that node violates the heap property. And if it does, then you're going to swap. I'm just going to keep going until it's satisfied.
So we need to make one copy, I made it 1.5, 1.5. One side is go off.
So at most, you're going to go all the way down to hit a leaf.
To this.
So another thing is like I have it with a bunch of copy paste in there, so it's like instead of having to return something like fruit at the end. I just have an extra line to it, like if I really wanted to.
I don't think I'm so cool here anymore. Just for my favorite.
It's more like
So you go here, like.
I mean, I don't know, I don't think about it.
I feel like a lot of it.
I always draw a picture. Yeah. When you go to university, I just because. Well, I mean, computer engineering is like an X.
Okay, so you're doing some coding?
Yeah.
So you got to do that to 274 again.
It's not like, it's not too crazy. Better.
No,
It's not too crazy.
it's better than to.
All right, cool. So if you didn't get a chance to practice, you can also try min heaping what you ended up with. A min heap is just like a max heap, except each node should be smaller than its children. And if it's not, swap with the smallest child. So if you have something like that, it's definitely not going to be a min heap, so you can go ahead and you can heapify using min heap property, and you should end up with a min heap. All right, so tomorrow we will talk a little bit about how we code this up using an array, and I'll show you the trick for doing all these operations efficiently. And then we're going to go on, we're going to start talking about dynamic programming, which will be PA 5, your last PA. All right, so I will see you next time.